right, second lesson of Unit 5, similar polygons and similar triangles. This is going to seem familiar a bit, or I should say, it's going to seem similar to what we did with triangles at some level when we talked about congruence. We talked about SAS and SSS and all that kind of stuff. It's coming up now. We're going to talk about similar. I think you've heard about similar before. Figures that have the same shape and are different size are called similar. If they're the same shape and the same size, they're called congruent. Let me give you an example in GSP. All right, this shape I just made looks like it's a pentagon. I've got this tool selected right now, so I can, if I can move stuff around, I can make it change size. But it's not really changing shape. If I was to measure these angles, the angles would stay the same. That pentagon and that pentagon, we say, are similar because they are related. They have the same size angles all the time, but they're not congruent, certainly. There's a big one and there's a little one. So that's the kind of thing we're talking about. For congruent figures, we could write, remember we wrote triangle ABC is congruent to triangle PQR, and that was, again, for congruence, that let us believe certain things about how A was related to P and B was related to Q, and that's kind of nice. For similar, we use this little symbol, and the gray box isn't really necessarily there. The little symbol is just supposed to look like the part that's on top of the equal sign in a congruent, which is kind of nice. I like that part about the symbolism. If it has, whoa, what just happened there? If it has the equals underneath it, we know it's exactly the same size. This little squiggly thing, I think this whole thing looks like toothpaste, like toothbrush and the toothpaste. Just the toothpaste part is the part that says they're the same shape. And it's a funny shape, so that's kind of cool. And if you make a statement with similarity like this, it tells us something about how C goes with P and O goes with E and all that kind of stuff. So here they're telling us, here's an example of one, CORN is similar to PEAS. So C in this figure over here kind of lines up with P in this figure over here. So we have two quadrilaterals here that are similar. And if you notice, it kind of looks like these are the same shape. It looks like they just took this one and they reduced it. Like they put it in the copy machine, they said reduce it. Or they zoomed out on the graph. Or here it is on the iPad, here is the same picture on the iPhone. And it's the same picture, just in different sizes. Not congruent, certainly. But here's where we get into the calculation and the so what. If two polygons are similar, then the ratio of the lengths of two corresponding sides is called the scale factor. And there is such a thing as a scale factor. We spent all that time doing ratio and proportion. This is why, because this is how these things operate. So, given ABCD is similar to EFGH, and this is nice because they did this one all in kind of copy-paste, parallel kind of order here. What's the scale factor of similarity between the figures? So what's the scale factor? What's the ratio between something over here that corresponds with something over here? Let's do that first. Well, I could say, looking at this naming system, 12 goes with X. Well, that doesn't really help me find the scale factor. Whoops. Doesn't help me find the scale factor because it's got an X in it. 5 goes with 2.5. Oh, okay, I can make a ratio out of that. We could say the ratio, remember a ratio is just something like this, is 5 over 2.5. Well, we should probably call that 2, otherwise we get laughed at math parties. 5 divided by 2.5 is 2. So the scale factor is 2, and then maybe you can kind of tell, like if I took this thing and just multiplied it by 2, I'd get that. That's one way to do that. If you were also to say, well, I don't like starting with 5 and saying 2.5 is on the denominator, I could start with 2.5 and say 2.5 corresponds with 5. That's also okay. And you're going, hey, wait a minute, I got an answer of 2 and I got an answer of 1/2. We would accept either one on that. Scale factor, it doesn't necessarily kind of denote if you're going from big to small or small to big. If you say 2, we know that you'd be taking the small things and multiplying these to make them big. If you have a number less than 1, like half, it means we're talking about the bigger things and multiplying by half, they become small. But it's the same, notice you get the same numbers. Those are the same, they represent the same amount of size change between those two figures. Reciprocals are kind of interchangeable here. And they'll be fine. You'll figure out why in a second. Find x, y, and z. Okay, so the deal with similar is then all of these corresponding sides are in that same ratio of 2. Or they all equal the same thing. So 12 is to x, like 5 is to 2.5, like y is to 3, like 10 is to z. Another way to say that, since this is such a nice scale factor of 2, each of these sides over here, they should each be double of each of the sides over here. Since this one's 2.5 and this one's 5, if this is x, when I take it times 2, I should get 12. Let me just write that. X times the scale factor ought to be 12, because that's easy to solve. X is 6. Similarly, 3 kind of talks to this y over here. 3 times the scale factor ought to be y. Well, that's helpful. And z times the scale factor. Notice I'm doing this carefully in the right order. Z times the scale factor ought to be 10. Now, you might have been able to do a lot of these in your head. Maybe it's not surprising to you that this is 10, this is going to be 5. If this is 5, this is 2.5. All the stuff over here is half of what it was over here. What's the perimeter of the two figures? Okay, well, y was 6. Let's compare perimeters just for fun, because we haven't talked about perimeter yet. 12 plus 6 plus 10 plus 5, sorry, is a weird order. 22 plus 11, this is 33, this perimeter over here. The perimeter over here, x was 6 and z was 5. If I add these up, 11, 14, 15, 16 and a half. Oh, looky there. That's also half. 16 and a half is half of 33. Those are also in the same scale factor. 16 and a half times 2 was 33. All right, so that's our first theorem. If you have similar polygons, the perimeters are in the same proportion as all the sides. So there it is written out in symbols. If this is similar, you can be sure that now not only does A go with J, we're kind of talking about segments here. So the segment connecting A and B kind of talks to the segment connecting J and K. So that's why you see it like this all the time. B and C goes with K and L. So the ratio of red over blue is the same in all these separate segments. But also, if we were to add them and talk about the perimeter, that's also the same ratio. In our last example, these ratios were all 2. Or they were all half if you put the blue one on top. That's the same thing. Here it doesn't look like it's 2. Here it looks like it's, I don't know. This one isn't a whole lot bigger than that one. This ratio is very close to 1. It's like 1.2 or something if you were to measure that by my estimation. Okay, given that this is similar, oh, this looks kind of spun around, so we really got to pay attention to what's going on. Wx goes with jk, I'm being serious. Xy goes with kl, etc. Find the perimeter of both figures. Okay, well, we'll probably have to figure out each one and see what's going on. It's not a bad idea to write these out. Wx over jk, xy over kl, yz over lm, and wz. Those would be the 4 sides of that figure. And I put those in corresponding order just right out of this thing. So then that kind of helps me go, oh yeah, okay, 17 over, that goes jk. All right, so that's over this thing down here. I'll call this x. Don't really know what that is. Xy, oh, I don't really know what that one is. Let's call that one y for now. That equals, well, that's not really going to help, so let's not do that one. I want something that's all numbers here. Yz over Lm, Yz is 20 Lm. Oh, good, let's do that. Yz over Lm. Notice how helpful that was to have one that's all numbers. It's always a good idea when you can figure this out, when you can start with one that's all numbers, because that's the key to telling you what all these fractions are equal to. If you have variables and a bunch of them, then it's kind of like, well, I can't solve anything. I need something solid I can sink my teeth into. So you look through this and go, all right, I need a number in this one and a number in this one. A number in both of them that tells me what's really going on. So I found that one here. 20 and 15 work because zy goes with lm. So that's going to be the beginning of the rest of the whole thing. All right, 20 over 15. I don't like 20 over 15. I want to reduce that right now. I don't want to call it 20 over 15. I want to call it 4 over 3. Make my life easier. Then I'm going to solve this proportion. 17 times 3 equals 4x. So 4x is 51. So x is like 12 and something, 12 and 3/4. Okay, so that's this side down here. Then these sides over here, what am I going to do? If I'm looking for this, so I found this x. To find this y, that's xy. Xy over kl, so that's xy. Over kl, which is 9. That also equals our favorite fraction of 4 over 3. When I found this out, this key fraction to be 4 over 3, I know that all these fractions equal 4 over 3. 4 over 3 is kind of the scale factor. So that means 3y equals 36. So y is 12. I'm running out of room down there. But I solve that and get y equals 12. And what's the last one I need over here? Yeah, I need this one over here. You know what? I kind of don't need this one over here. I'll show you why. Let's do this perimeter. The question was find the perimeter of both. So the perimeter over here, oh my gosh, okay, 20, 32, 42, 49, 53, I get 73. If that's the perimeter over here, what's the perimeter over here? Well, I could go to the trouble of finding MJ, or I could just go, you know what, this perimeter is this much scale factor bigger than this, so I could just do that. I could just take 73, that's the big one, So I want to kind of divide it by 4/3, 4/3, and I'll get the perimeter over here, which is not easy. Calculator time. All right, I figured that out in the calculator. I get 54.75. So that's enough. I could have found MJ if I wanted to. It would have actually been maybe a little easier to do that. I just want to show you that trick. All right, two polygons are similar, if and only if. All those angles are congruent. All the corresponding angles are congruent. So if you're trying to prove this is similar to this, you need all the angles to be congruent, and you need all these sides to behave as such. You need them all to be proportional. In order to show two triangles are similar, you don't have to show all that stuff. Remember when we proved triangles are congruent, we didn't have to show that every single side was congruent to every single angle. We were able to identify that there were certain sub-collections of that were nice shortcuts for showing that the whole things were congruent. There's a few of those for similarity. Here's an interesting one. Two angles. If two angles of one triangle are congruent to two angles of another triangle, then it turns out all of the rest of this definition of similarity, or this kind of biconditional similarity, will have to fall into place. We know already that the third one will have to be true, because the third one will have to match because of the 180 in a triangle business. So if you knew two angles, you kind of know what the third one is because of 180. So if you knew these two, you'd know that all three of them would match. But it turns out that that also ensures that the corresponding sides will have to be proportional. Only works in triangles, doesn't work in other shapes, but if you know the angles of a triangle, you can really tell what shape it's going to be. You can't get out of making a triangle that is going to be the same shape. They don't really prove that here, and I'm not going to do it now, but you got to believe that angle is enough for similarity. Here's some more. Side, 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 and side, angle, side. The way they name these is just like they did for congruence. However, don't get too comfortable. Don't be like, oh yeah, I know what side, side, side is. I've done that before. It's a little different here because here we're not talking about sides that are congruent. These two red sides are not congruent. We're naming them. We count them in our proof. They, their count is one of the sides, and these, it's side, angle, side. Great. But here, we're not trying to find sides that are congruent. We're trying to find sides that are proportional. So side, side, side means that we've determined that all these sides are in the same proportion. The fraction of the comparison, sort of the scale factor, is the same for all three sides. For side, angle, side, it's a little trickier to think about because, again, we're thinking of these sides that are in proportion. So red over red equals blue over blue. But with angles, remember in similarity land, angles are congruent. So, this is a little tricky to think about this collection, side, angle, side, where the S's we're talking about proportion, but the angles we're talking about congruence. I guess the good news is this is kind of the end of the list. It wouldn't make sense to talk about things like angle, side, angle, or angle, angle, side, because guess what? Those are taken care of with this. So having two angles on a side doesn't make sense. Also, having one side proportional doesn't make any sense. To have sides that are proportional, you need to at least be talking about two, because we're talking about comparing two fractions. You can't really do that with one pair of numbers. You need two pairs of numbers to fill out a fraction proportion. You need four numbers in there. So they're always going to have two. So the only thing left that you might possibly think about would be that one that didn't work in congruence, which is the SSA, also doesn't work in similarity for the same reason. So the whole similarity list is exactly the same thing. You might be thinking, well, what about HL? Our book doesn't use HL for similarity, and kind of doesn't have to, and we'll see why. Okay, example. Do I have time for this? I know I'm going to have to break this into two videos. There's a lot going on in this. Yeah, this is the, are these triangles similar? Guess what? This is the one where there's, 5 or 6 problems of this at the end of the notes. So guess what kind of problems you're going to see on the test? Pay attention. All right, the question is, can we arrive at angle, angle, or side, angle, side, or side, side, side with this information given? Okay, so are there triangles congruent or similar? Well, the only two triangles I see in this picture, the only two possible triangles that might even work, let's just write them in and we'll cross them out if it doesn't work. CDE is a triangle, and we're questioning this similarity right now. CDE might be similar to CAB, or some twisted up version of that, but those are the two triangles I see. Well, what's good about this, angle C and angle C already go with each other. We have a reflexive angle C here, so that's good. So already I'm thinking we're probably going for angle, angle, or for side, angle, side. Oh, but look, these sides are labeled. So if we're headed for side, angle, side, and again, I'm just kind of questioning. Let's see if that's true. There's an implied question mark here. If that's going to be true, we've got the angle taken care of already. We need these sides to be proportional. So the side of CD we're talking about is 6. That would have to go with the corresponding side of this triangle, which is CA. CA is 9. So I'm just going to write this here so you can look at this later and go, oh yeah, that's what he was doing. Oh gosh, I'm going to run out of time. See you in part 2.